Hello guys and welcome to a video on Bresenham's line drawing algorithm. So what is Bresenham's line drawing algorithm and how to draw a line? We'll be going to that first. We'll know about the basics of drawing a line and then we'll get into the algorithm and how we can utilize it in drawing a line. So the basics. Any line can be represented by using the equation y is equal to mx plus c. I hope this is known by all, where m is the slope of the line and c is the y-intercept of the line. So in our basic graphic system, we have the y-axis, x-axis, this is the x, this is the y. So any line segment now, assume this thing. So it has values of x and y and slope. So where m can be calculated as delta y by delta x. So what is delta x and delta y? These points I'll rename x1, x2, y1 and y2. Now we can calculate what delta x and delta y are. So delta y is y2 minus y1 and delta x is x2 minus x1. By this we can calculate the slope of the line. Now based off the slope, assume a line makes an angle of 45 degrees as such. So this is 45 degrees and this is the y-axis, this is the x-axis. Now we can say that the difference in the x points and the y is the same, right? So basically delta x is equal to delta y. As a result, m is equal to 1. If you substitute x and y here, you get the value of slope as 1. Now similarly, if the line goes under this is slope, we can say that the slope is less than 1. Or we can say the difference in x is more than the difference in y points, right? And again, if the point or the line basically goes upwards, we can say the slope is greater than 1. So for these, the difference in x is smaller than the difference in y for this one, and the difference in x points is greater than difference in y, right? For now, we'll be looking at how we can implement the Bresenham's algorithm, the line drawing algorithm, for lines having slope lesser than 1. So obviously we can implement it for lines greater than 1 and 1 as well. It's just the point of changing how we use the values of x and y in the algorithm. So we can use these values and generate lines. Moving ahead, any line in the coordinate system can be defined by the line equation y is equal to mx plus c. That's known. But this is not useful directly on a display device or a screen. Now, first things first, your screen. This is your screen. Your screen is made up of, a collection of pixels, you could say. We have basically the computer has the origin right here, takes this as x-axis and this as the y-axis. So we are used with using the origin right here and taking this as y-axis and this as x-axis. So we'll be using what we know. We'll be taking this as y-axis, this as x-axis, and this as the origin, and plotting the line however we can, and then converting it to how a screen uses those pixels to plot the line. Now, pixels. Okay, basically we have our coordinate system like this, and we have lines, right? We have lines, a line segment. This is x1, x2, y1 and y2. We have this. So how do we plot this into this? So this line is basically drawn using the equation y is equal to mx plus c. So how do we use this equation to plot lines or to draw a line on your screen, which is made up of pixels, right? So this is a vector, you got to remember. See, so I've said it's a vector, and as you know, a screen is a collection of pixels, or rather you can call it a raster, a collection of pixels. So now we got to convert a vector into something called as a raster. So the process is rasterization. So how do we do it, right? We have to define a line as a collection of pixels. For example, okay, to say we give a starting point and an end point. Now, this is a starting point and this is the end point. So we can draw a line from here to here. These are all pixels. Note that this box is one pixel, this is another one, and so on. So we can define a line as a collection of pixels. So what we have to do is now convert this vector into raster, also rasterization. How does this rasterization work? How do we get values of pixels from the equation y is equal to mx plus c, right? Now, as you can see, we have two unknowns in this equation. That's y and x. Like, how do we get both values and then plot? That's impossible. We need another equation. So what we do is a simple trick. We use sampling, or not sampling. Sampling. Okay. As you know, I said m is less than 1, right? We'll be calculating, or we'll be using Bresenham's algorithm for lines less than 1 with slope less than 1. And then we can implement it for lines greater than 1 also with slope greater than 1, basically speaking. As you know, if a line slope is less than 1, the difference in x, that is delta x, is greater than delta y. That is, the difference in these points is way larger than delta y. See, you can see this is smaller and this is large. So we have a lot of points here. What we do is now in this equation, we provide the values of x. So we keep incrementing 1, 1, 1, 1, 1, and then we get the corresponding y value to be plotted right here. And then we use that to plot lines on your screen, basically. So for example, I have a line something like this, graphically representing like this. So this is your x and this is your y-axis. So for this, we have slope 0, right? So y remains constant and values of x keeps incrementing. That is x1, this is x2. So if I substitute this into this equation, we'll be getting values of x, so that we can plot it right here. So it gives you the straight line, right? Assume these are your points and we get a straight line. It might look something like this. 1 second. So once we plot it on your screen, so we decide what pixels to be illuminated, right? Might look something like this. So we illuminate a straight line of pixels and you get a line, right? Simple as that. Now assume we have another line. Example, a line of 45 degrees, right? When it's 45 degrees, we know the slope is 1. This is pretty simple. We can plot this also. We have difference in x equal to difference in y for this one. If we plot that, it's just a straight line. So it'll look something like this. Yeah, we have this pixel illuminated. We illuminate this pixel and so on all the side pixels. Illuminate this again. So you get the point, right? We illuminate this and keep going till the endpoint is reached. I said we draw a line between two fixed points in Bresenham's. It looks something like this. So we have a line with slope 45 degrees. Now the problem arises when, assume, I'll erase all of this for better understanding. So yeah. Now assume that I need to draw a line from, okay, assume 1 comma 1 here, that is this thing, to assume 5 comma 3. So 5 comma 3. If I draw a line now, this to 5 comma 3, that's right here, I'll draw a straight line. So as you can see, the line that I've calculated, it goes through 2 pixels at the same time. So you can see here, right? This is where a problem comes into play. So your screen needs to decide whether to illuminate this pixel or this pixel. It can't illuminate 2 pixels at the same time. It would look not good, you know. Line might look like this. So you don't want your line to look like this. Now see, at this point, at point 2, the line is passing through this pixel as well as this pixel. So your Bresenham's algorithm or any algorithm must decide which pixel to eliminate, right? Now, let me tell you this thing. Pixels are integer value. They have integer values 1, 2, 3, 4, 5, 6. They don't have float values. You can't say 1.5 pixel or 1/3/4 of a pixel. It's impossible. You can't do that, right? So this is where you use Bresenham's algorithm to decide which pixel to eliminate. So moving ahead, yeah, the idea behind Bresenham's line drawing algorithm. Now, the idea behind Bresenham's algorithm is to avoid floating point multiplication and addition to compute mx plus c, that is your equation of a line, and then compute the round value of mx plus c in every step. So what this says is basically we have another algorithm, that's DDA algorithm, if you know about it, to compute which pixel to eliminate. We utilize division. So the problem with division is that once you divide, you have a probability of getting fractions, right? And fractions in computer terms is represented using float. Yeah. Okay, that's okay. Float type output. Now, float is a way to represent fractions, as you know, but pixels are integers, right? You can't say, as I said before, 1.5 pixel or 1/3/4 of a pixel, 1/2 pixel. You can't say all these. It's either you select a pixel as a whole or you not at all select. There's no pixel at all, right there. So that is how you represent pixels. You eliminate it or you don't eliminate it at all. What DDA does basically is it computes every value. So to make the decision right there, it's a float based algorithm. Like you use float or fraction or division to compute the next pixel to be eliminated in drawing line. So we have 2 points and each pixel to decide use division, and then a float point is produced and you use that to decide, okay, you eliminate this and this. Now when such above case happens, when it travels to 2 pixels, the drawback occurs. You use float, then you again round it off to a decimal point value or integer basically. So from fractions to integers. So there's a conversion between them. So that's a drawback. And then you use float in your operation. So once you use float, it's pretty slow in operating. So algorithm's time goes down. So this is one drawback. So to avoid all of this drawback, we use Bresenham's algorithm. In Bresenham's algorithm, as you know, we move the x-axis, as I said before, m calculate less than 1 for lines. Move the x-axis in unit intervals and then we calculate the y value. In Bresenham's algorithm also, you need to know that in DDA, we get a crude line, whereas in Bresenham's, we get a smooth line. So it's smooth, there's no sudden, it's not like that and stuff. That's one major difference. The idea behind Bresenham's line drawing algorithm. Now, when a line goes to 2 pixels, as you know, as I said before, when it goes to 2 pixels, okay, yeah, we took, we assumed 1 comma 1 and 5 comma 3, 1 comma 1 and 5 comma 3 right here. So assume I'm drawing, so there you go, it's going through 2 pixels right here, this pixel and this pixel. So at the same time we assume that the line is going through the space between those 2 pixels, right? Now in real life speaking, pixels are not spaced out, like there's no much space between every single pixel. It's compact in your screen or any display device speaking, but we assume that the line is passing through the space in between them so as to ease the calculation method. So as you can see here, we'll take this pixel as a point right here and this pixel will take it as this point. So while drawing a line, you can see it passes through the space. This is the space between two pixels, the distance d, which represents the space. So yeah, we always increase x by 1 and we choose about next y, whether we need to go to y plus 1 or remain on y. In other words, from any position x of k, y of k, we need to choose between x of k plus 1 or y of k and x of k plus 1 or y of k plus 1. So what this says is that, assume you have a line like this. You have a line. Once you zoom into it and you can see the smaller details, it might look like this, right? The pixel values between 2 points. Now you got to decide if the line is coming like this, and do we need to step up one y value, or do we just stay in the same y value? You come here, or do we change it and go, or come, stay in the same y value and continue? So that is what Bresenham's algorithm does. And how do we decide? How do we decide whether we jump one y value or remain in the same y value? That depends on the decision making parameter, also called as pk. Not called, it's represented by pk. Now, you can see here this line, the line, this line I'm telling you is not seen on the screen. It's calculated and plotted. So I said to you before, assume this is the line. This is not plotted on the screen. The difference, this distance, assume it as d1 to the actual line, that is this one, and d2. This is the distance. So what Bresenham's algorithm does is basically it illuminates the pixel that is the closest, that is having a distance that is very short to the actual line. This is the actual line. Now, how do we do this? We do this by two factors basically, d1 minus d2. So d1 minus d2, we minus them, and if the output is lesser than 0, that is negative, we say that then it's y of k. So this is selected. Why is that so? Because if you get a negative value, d1 is smaller. It might be smaller. It might be here. Line may pass through here. So we eliminate this pixel. And second factor is d1 minus d2. So this representation basically. So we minus distance d1 with d2. So if it's greater than 0, that is positive. So value of this minus this might produce a positive result. So then we said that d1 is greater. So the distance d1 is too much. As a result, we'll take d2, which is having a smaller distance. So this pixel is eliminated. So this is the way we make decisions. And how is it done in the algorithm? We'll just have a look. So this is the algorithm. We'll have a starting coordinate and an ending coordinate. As I said before, works between two coordinates and draws line, making decisions at each pixel. At each point we make decision, and then as a result the output is a straight line or a line basically. So the start coordinate is x naught y naught. Okay, there is a typo here. It's x naught y naught. So let me do this for better understanding. So start is x naught y naught. End coordinates. So the coordinates of the endpoint is xn yn. Right? This is your y-axis. This is your x-axis. So we'll keep incrementing x by 1 unit. That is, we'll keep incrementing it by x plus 1 and keep going forward. And corresponding y value we'll calculate using the equations. So calculate delta x and delta y. As I said before, so delta x's value is xn minus x naught. So xn minus x naught, the difference between the endpoints, and y is yn minus y naught. So once you get this, we can proceed in step 2. So as I said before, decision parameter, this is very important. So pk is given by 2 delta y minus delta x. So this thing you got to remember, it is used to find the position to or point to draw the line. So it's not directly plotting the point, it is used based off of the value of p of k. We decide whether we go to the above pixel or remain in the same y pixel. So that is how pk is used. Step 3, calculate the next point in the line depending on the value of the decision parameter, as I said before. Now we'll assume that the current value of the point, so we are here at this point, so we need to calculate the next point, right? Do we need to eliminate the above pixel or the below one? So we'll assume this point as x of k, comma y of k. This point, the point we are in, and the next point is x of k plus 1, y of k plus 1. Now assume it might be either this one or this one, but we'll just take it as x of k plus 1 and y of k plus 1. So the value of x of k plus 1, y of k plus 1 depends on the value of p of k. So yeah, will depend the value of this point. It might be this or this. So we'll decide which to select based off the value of p of k. Now two cases arise. That is the decision making. So if p of k value, so as you know, you calculate p of k like this. Now if p of k's value is less than 0, you'll p So the pk of 1, this is used to decide the next pixel. So it's p of k plus 2 delta y. And xk of 1, that is you keep on incrementing x values with the next value as it's known, and the yk plus 1 value, you'll keep it as the same value. That is, you go in a straight line, you don't take a shift, you keep the same y value. Whereas in case 2, if pk's value is greater or equal to 0, so you recalculate p of k plus 1. So p of k plus 2 delta y minus 2 delta x. So you use this. This is for the next one, next pixel right here. And then xk plus 1, as you know, you'll keep incrementing x value. And then what y value should you take for the corresponding x value? So it is xk plus 1. So you come here and increment in the y pixel and then continue, or depends on the next case. So this is how the decision is done. Go straight. In this case comes and increments in y. So it looks something like this, something like that. So in this, it's a straight point in this increment. Whereas this thing is, you can say, a step up in the thing to draw a cross line. Step 4. So this is the last part of the algorithm. So we repeat step 3 until the endpoint is reached. As I said before, 2 points. We keep on doing that until we reach x of n, y of n. That is the endpoint. So once this is reached, you stop with your algorithm. So thanks for watching.